Okay, we can start. Good afternoon again, and yeah, welcome in this our third event for this meetup. Today we want to talk with you about industrial automation. How can we use IoT in industry sector. Usually I am here with Stefano Tempesta, the other co-owner for this meetup, but today he has some issue with the job. I am Alessandro Graps, CEO in JouleHub. It's a Switzerland company specialized in R&D and digital transformation in electronic, robotic, and mechatronic sector. Today we have a guest, Pedro Nora, that talk about Industry 4.0. After he can introduce yourself, etc. And I talk about digital transformation in industrial automation. How can use IoT predictive maintenance in manufacturing industry. That is our next event. Today is our last event for this year, and after the holidays, and in the next year, I hope that will be better than that. We can come back again with our event, and the next one is about farming. How can use technology, predictive maintenance, IoT sensor inside the farming sector. Just some words about industry and IoT. What we can see, especially in this current year. I talk about Switzerland and Italy, where we, especially in Italy, we had some issues with the lockdown during the COVID pandemic. And we can see that more company, more our customers start to implement and to understand better what is digital transformation and how can prevent and help the business. 45% of the company in Italy are filed, and the other company can still alive thanks to the digital transformation. Digital transformation meaning robotic, predictive maintenance, predictive reaction to manage the company or the business process in with automatic process. We can, after I can talk about our use case, where before the pandemic we implement in our company all robotic, all digital transformation in production, electronic circuit board production, and they can work during the lockdown without close company and without have any people inside. Good. Perfect. I pass the headphone to Noah, and okay, you can share your screen and.
Thank you, Alessandro, for the introduction. Hello, everyone. Thank you for joining us. My name is Pedro Noronha, and I'm a mechanical engineer from Portugal, currently working at Connecting Software. We are a company specialized in developing software integration solutions. And let me share my screen very quick. Okay. Let me know if you can see. Can everyone see
Yes.
the? Okay, good.
Yes. Thank you.
Let's get this started then. So today I want to talk to you a little bit about Industry 4.0 and what we, Connecting Software, are doing to make it reachable by everyone. So I like to start with a question. When was the last time that you bought something from an artisan? Nowadays, the skilled craft workers only targets the low volume and high-end cost of the market. But for most of human history, this was the only type of manufacturing that existed. Technological developments in the end of the 18th century allowed humanity to harness steam power, which led to a huge increase of worker productivity as manufacturers moved away from hand production methods and into mechanical production. Towards the end of the 19th century, another transformative force came into play, electricity, and its widespread use in factories allowed for true mass production to emerge as a viable option, as machines could work around the clock without any breaks. The later half of the 20th century saw the beginning of the computer era and the rise of industrial robotics. This allowed for repetitive production processes to be automatized and monitored remotely, increasing production outputs and, most importantly, production quality, as machines could perform the same task over and over with incredible precision. And following these three preceding technological transformations, we are now on the verge of yet another industrial revolution, which is what's commonly known as Industry 4.0, which is the new buzzword in manufacturing. So, if you ask anyone you know about Industry 4.0, you will get a lot of terms thrown at you. Smart factories, big data, cloud, AI, industrial IoT, etc. And these technologies, and I'm just really touching the tip of the iceberg, do not make up Industry 4.0 and should only be considered as enablers, as a means to an end. In a very general sense, I like to define Industry 4.0 as an information-intensive transformation of manufacturing and other related industries into a connected environment of industrial assets, processes, people, and systems that leverages the generation and usage of vast amounts of data into actionable information. Industry 4.0 promises improved productivity, efficiency, flexibility, and a more dynamic approach to production. All of these advantages will lead to a higher return of investment and increased future profitability. People should realize, however, that this is not something that will happen overnight, and companies should not try to implement all the technologies at once. In order to move to a more intelligent manufacturing, smart factories, connected industries, whatever, you first need to bridge things such as industrial assets, people, and work processes. And to bridge all that, you need strong data gathering, integration, and networking. Everything must be interconnected and interoperable. Interconnectivity would mean connected devices, connected communication technologies, connected people, connected data, and interoperability implies collaboration, ability to have many standards talking to each other, so data from several sources can be leveraged. All in all, unified and holistic information from every single source. But for right now, let's move away from Industry 4.0 to give a little overview regarding automation in a factory. In the shop floor, most of the machines that you will find will be controlled by a PLC, or a programmable logic controller. These are small industrial computers that have been ruggedized to withstand the harsh conditions that are often found in the shop floor, and they are used to control manufacturing processes such as assembly lines, machine functions, or robotic devices. They generally consist of a power supply, a CPU, an input-output module, and a communication module. They capture the data from the plant floor by monitoring its inputs that come from sensors or other field devices, and then the CPU executes the user-created program logic and outputs data or commands to the machines or other actuators that it is connected to. A common method of connecting these field devices to the controller is by using a 420 milliamps current loop, which is an industry standard. But although it's effective, it has a major drawback. Field wiring can be very excessive, since one wire needs to be connected to a field point and then to the centralized controller. And it's this issue plus others that spark the movement towards a unified field bus. Field bus is an industrial network that is specifically designed for communications between PLCs or between them and the field-mounted sensors and actuators. It's designed to replace this point-to-point wiring that connects each sensor and actuator to the controller input and output module. I can pass this very quick. Okay, and industrial control networks can be broken up in 3 distinct generations with several levels of compatibility. The first one is the traditional serial-based field bus protocols. The second, the Ethernet-based, and more recently, the last generation would start incorporating wireless communication technologies. Some examples of well-known serial-based field buses would be Modbus RTU, Profibus, etc. Well-known Ethernet-based protocols, Modbus TCP, Ethernet IP, Profinet. By having this big, diverse selection of protocols, a field bus can be chosen for a specific task at a cheaper price and lower complexity. Like I mentioned in the beginning of the presentation, central challenge of Industry 4.0 and industrial IoT is the secure, standardized exchange of data. And different types of industrial communication protocols don't always play nice with each other. This means that all devices on a network would have to use the same type of communication protocol, which prevents the interoperability of all equipment, even though most companies try to keep it to a minimal number of vendors. In order to solve this, in 1995, a vendor-independent industry group, the OPC Foundation, developed the OPC standard to help address this challenge. The OPC standard was designed to provide a common method of communication between field devices and software applications. The OPC server talks to the PLC or other field device over its native protocol and then converts that message to a standardized format defined by the OPC specification, which can then be read by any OPC client. So an OPC server could be viewed as a software application that converts different protocols into a common language that then any client application that needed that data could understand. Like I said before, or I can jump this quickly. Let's, for example, suppose that we have an OPC client that wants information for a certain PLC. The OPC server would communicate to the PLC using the Modbus protocol. The server would ask for the specific memory address that contained the data, and then the PLC would provide all the responses that the OPC server needed using Modbus as well. The OPC server then converts the data to the OPC format and sends that data to the OPC client application. So OPC client can get data from the server without having to know anything about the PLC or what is its automation protocol. Now, when I'm talking about OPC, I am strictly referring to the OPC UA, or Open Platforms Communication Unified Architecture, which was a framework that was released in 2008 and builds on the success of the OPC Classic by being functionally equivalent, but providing much more features. It has a service-oriented architecture in which the servers, known as data providers, expose the information model to the clients, data consumers. And one of the biggest strengths is it can be used on different platforms, Linux, Windows, Android, etc., while the previous OPC Classic could only be used on Windows machines. During the development of the OPC UA standards, the highest degree of safety was taken into account from the very beginning. It's firewall friendly, it can be controlled and steered via standard network techniques, while OPC Classic relied on the DCOM technology. It does not only offer common IT mechanisms for authentication, signing, and encrypted access, but the actual transport layer can be extended by additional protocols at any time. When a request is received to connect to a server, the server validates the request, decrypts it, and then validates the certificate. Once a valid request for authentication or authorization is received and decoded, the next step is to determine if the server should accept the connection from that device or allow access to that user. So It's very safe. It's designed to counter threats that are most likely to occur in your manufacturing plant. So this isn't to say that OPC UA is better than Internet IP, Profinet, Modbus. For moving input-output data around the machine, these protocols, they provide the right combination of transport, functionality, and simplicity. And they are very good technologies for machine control. But for moving information up from the field to the business software, OPC UA increases productivity, quality, and lowers costs by not only providing more data, but also information and the right kind of information to everyone that needs it. Another big challenge that Industry 4.0 is facing, or its real scale implementation faces, is the legacy barrier. Most automation devoted devices, for example PLCs, they are expected to have a lifespan of many decades. So the advance of innovative technologies like those brought by Industry 4.0 strike the legacy of the already existing facilities. As it's clear, investors' association with modernizing both software and hardware are a very serious obstacle. Most companies, they refuse radical modernizations or simply cannot take the risks of quitting a running system. Why change if it's working? So the integration of new advanced components within production systems requires a very good migration path to Industry 4.0, in which people should follow a step-by-step process instead of trying to change the whole system at once. Due to the networked operation in Industry 4.0, machinery and equipment should be provided with data sharing mechanisms. In other words, connectivity is a key feature for the legacy of already existing infrastructures. Therefore, a first stage on any migration to Industry 4.0 should be adding network connectivity to the current devices. And it's possible to do this with the use of OPC UA servers, whether embedded in the devices for the newer ones, or by using the servers as standalone software. By using this, number of brands and devices that can be interconnected includes the vast majority of the hardware on the field for almost every industry. Even PLCs that communicate over serial field buses can be connected to an OPC UA server over a server gateway software or gateway devices. And this means that companies can take their first steps into Industry 4.0 with, in many cases, minimal investments. Like I said earlier, manufacturers need to easily access data from their production process as a way to identify, analyze everything that's happening and really leverage the power of machine learning, AI, and big data. Let's call it an IoT platform would aggregate real-time data from the hardware and then would make it, how do I say this, accessible by a wide group of users. It should bridge the gap between the hardware and the software and the people by putting everything into a centralized system, either on the edge, either on premises or on the cloud. Okay, so now for a little story from my time working at an automotive industry and why it's so important to have a very sound migration plan. It's not enough just to connect all data from the PLC, all PLCs to an OPC UA server and you are ready to go. If there's not an assessment of what data you want to obtain, how you want to connect this data and use it, how to deal with the commissioning and decommissioning of existing or new devices, the Industry 4.0 project will likely end like all the others, where most companies get talked into by a smooth talking salespeople into investing thousands and thousands of euros on software that reads machine data, presents it information in a dashboard that can be checked by everyone. And for a few months, even a year or two, this works just fine. But then a new machine gets bought and no one knows how to connect it to the new system, or a part stops being manufactured, production line needs to get changed to cater to different needs. And once again, no one knows what to do. Or maybe they get a new business software and they cannot connect the software to this platform. Maintenance could probably help, but they're always swamped with other things to do and don't have time to reconfigure everything. IT department is the same, and little by little, the software, the platform stops being used and likely remains that way until when someone from the higher ups remembers and tasks an intern with making the factory adopt it again. And just like that, Industry 4.0 was forgotten. So testing the first prospective applications of IoT platforms should not require a long preparation or a large upfront investment. Or I'm kind of contradicting myself, but doing the first steps in a correct, following a plan way should be easy. And several years ago, a lot of major industrial vendors tried to build general purpose platforms, and hundreds and millions of dollars later, they scaled back these initiatives for special purpose scenarios. Even competitors in the same industry, they can have different requirements, different goals. So trying to provide something that fits all is not easy. And how can you win if you're stuck with the same capabilities and limitation like everyone? You should, I wrote this here, you decide to look for a faster horse. I say you need to stop looking for a faster horse. It's time to build a flying car. So this data integration challenges is the type of problems that we try to solve by connecting software. Our world is a place where systems and applications can communicate in one universal language, a world in which data is available at all times, irrespective of its origin or destination, form or purpose. In this world, interoperability is not just a buzzword, but rather a unified, everyday reality. We are striving to build a universe that enables developers to seamlessly integrate data from any source to provide the ultimate insights to end users. And that's exactly what we achieved with ConnectBridge, which is our powerful software integration platform. And by using ConnectBridge and our more than 400 connectors to most popular and widespread industry and business applications, developers can securely connect to a wide range of business softwares via their APIs, but without needing to learn the documentation. The architecture that we use enables communication via SQL, which is a programming language that every developer knows, even the most junior ones. And what ConnectBridge does is translates the SQL syntax into the appropriate API calls. And this way, we can keep the target system's integrity secured while offering the ease of communication between your application and your target systems. And in order to extend this to the industry world, we decided to develop a connector that would allow us to speak machine language. So what we did was we learned the OPC UA architecture and then we mapped it into SQL. So right now, what this OPC UA connector that we developed does is it works as an OPC UA client. This means that if we have an OPC UA server address and the correct permissions, we can access data from any OPC UA server. After the connection was established, the data that the server exposes can be interacted with using SQL. So a developer working for a company could easily integrate the company's shop floor data into any business software that they use, creating a custom-made solution tailored to their specific needs. So I will stop the presentation very quickly to try and show you a little demo that I prepared. It's very simple. I don't have a very big development background. So what I did was I connected to a OPC UA test server, which has some variables, and then I displayed that data on Excel. Let me quickly try and change the window. New share. Screen 2. Okay. I will wait just a few seconds to see if this is showing up, but I assume it is. If you're not seeing my screen, let me know. So here I have the ConnectBridge Management Studio, which is our platform to configure the connectors. And I already pre-configured here.
Sorry, Nora, we see only your slide, not your PC.
Oh, yeah. I figured the problem now. I forgot to click
Yeah,
share.
perfect. Thank you.
Is it working now? Can you see the?
Yes, yes, perfect.
Okay,
Thank you very much.
good. So here you can see, I will highlight it. We have an OPC UA connector. So what I did was, you open this. Here is an address from a server that I connected to. This is a test server. I'm not connected to any company right now. I'm not using any type of not a certificate, not a username-based authentication, because I don't need to for this example. So simply what I need to do would be set up the connection to the server. And now my goal is to display the server. What's happening here? I chose to measure two particular points, the humidity of one of the sensor and the temperature. I did a very simple macro that I can show you here quickly, in which this is the most important stuff, which is where I establish my connection. In order to get this, I would need to come here. It's not very interesting, but I would get connection string. This is generated after I configure it. Simply copy this into here, and I'm good to go. And then I'm reading the attributes of humidity and temperature, and I will get to here in a bit. So very simple. I set it to give me the data that it's measuring every 2 seconds, but this is just really to show you how simple it would be to connect to the server and read information. I'm giving a rather simplistic view. There will be some challenges coming from connecting the PLC to the server, but there's plenty of software on the market that does just that in a very straightforward way. Okay, I will change my screen again just to wrap up the presentation. Share. Okay. So this connector is still not completely done. There's still work to do. Our vision for it is to turn it into a full-fledged, highly customizable IoT platform, ready to connect the shop floor to the manufacturing execution system, to your ERP or any other business software that the company has. However, there's still a lot of work to be done. The platform needs to be above all user-friendly. And one thing that I didn't tell you was these two temperatures, the temperature and humidity that I showed you, I would need to know what was the node ID, the particular piece of identifier information. Right now, my connector, this client that we developed, doesn't have a graphical user interface where I could check the tree structure and then say, I want that node ID. I'm using another OPC client that has this functionality to test our results. But one of our next steps would be to implement this function. Furthermore, an OPC UA server can have information from a lot of devices. So in my opinion, it would be interesting to have a way to organize the devices in a sort of a hierarchical way. So this company, this specific plant, that specific line, that machine, that controller, that sensor. And this can be done already by following the references between the nodes. But my goal would be to have a more visual and organized approach with this, so that I could, or a customer could do a lot of calculations, could be done on the platform directly and stored in the corresponding hierarchical place. That way you can do the calculations on the edge and then only send upwards the necessary information. Also, any other applications that needed this data can always get them from the same place. Following this, all data that is readable in the devices should be uniformized. So if two different devices provide information about two different temperatures, the values shown should be shown using the same units, the same scale, and the same, although differentiable, labels. A lot of OPC UA servers might exist on a factory floor. And right now, in order to connect to a server, you need to manually configure the connection on the connect bridge, like I showed you. But in the future, there's a service that OPC UA provides, discovery service sites, that's used to discover other OPC UA services, servers on a network, needs to be implemented. And it wasn't on this first iteration of the connector. More importantly, something we do not have and you absolutely need, alarms and conditions needs to be configured as well, because the ability to set alarm points on each device and alarm parameters and the alarm limits is absolutely necessary. Finally, I also want to include publisher subscription messaging, so we can allow instantaneous push-based deliveries, eliminating the need to poll data or check for updates. So lots of work to be done in order to make this IoT platform plug and produce as much as possible, but that should be what we strive to do. And so that only minor configurations would be needed from the customer side. But even with these shortcomings that we have, we believe that this OPC UA connector is on a pretty good path. It allows companies to take their first steps in the digitalization of their businesses and of their shop floors in a very affordable way. It's no longer just something that the big players, the big companies that have a dedicated IT department can do, but now it's also starting to get open to small and medium companies that sometimes have the so-called one-man show IT departments. And that's it from my side right now. If you have any questions, feel free to ask. If there's something that I do not know how to answer right now, here are my contact details. Write me an email. I would love to get back to you.
Okay, thank you very much, Nora. We have from chat, from Dan, one question. I read you. Isn't it that OPC UA can also bring data exchange up to the cloud level?
Sure, it can, for sure. One of the biggest advantages of OPC UA is it provides information model where everything is standardized. It's completely possible to do that.
Okay, thank you very much. Other question? No, by chat, we don't have any other question. And yeah, thank you very much, Nora. It's a very, very interesting point. And
Thank you for the opportunity.
Yeah. And now I share my screen for the other presentation. Just 1 second. Okay. Please say me when you can see my screen. Okay, now it's better. Can you see my screen?
Yes.
Okay, perfect. Thank you very much. And yeah, today I would like to talk about the digital transformation in industrial automation. How can implement all sensor, IoT, predictive system, remote assistance in industrial automation, and what we can do. Before to start, I would like to talk about react or prevent. What meaning? In industry, especially in this last year, we can see that people understand if must be a company to react in a quicker way, or a company can prevent something. What is the difference? The difference is that machine during a prevent process can understand what is a problem, can understand how can solve this issue, and can also calibrate to have high performance with a minimum power during the productions process, for example. React, what is React? For me, it's a legacy situation, what the company have now, meaning that when I have a problem, I have React. Doesn't matter if I can prevent, but I really don't need to know if the problem will arrive. Just only to react to solve the problem when the problem is visible. I can say what is the right process, but because there are different situations in the company, there are different process, etc. But for me, it's important that the company can understand the issue and give the possibility to be relaxed, to remove all stress around the process, production process. But what meaning maintenance, predictive maintenance? Sorry, predictive maintenance meaning for me is monitoring equipment. All equipment is under control. The equipment can understand what are the issue and what are the maintenance process inside the machine, for example. Schedule maintenance, for example, when the machine needs, without schedule every 6 months or every quarter during the year. Because without predictive maintenance, the company need to schedule a fixed maintenance process where they blocked the processes and they change pieces inside the machine without understanding, without know if the machine really need to change this piece, for example, or identify the causes of the issues. What is the really issues, to understand if it's a generic issues, a periodic, is a constant issue, and in which model we can do that. With a predictive model and the sensor data, because we need to know and we need to know that the main actor in a predictive maintenance is all digital transformation are always data. Without data, we cannot do anything. And deployment, the equipment, and the information on the cloud to give, to share this information with all machine and all processes. But why we must predict? We must predict to have a low cost of maintenance. We must predict to extend the life of the machine, reduce the downtime, improve the production, because we can predict also the performance and the machine can calibrate without human process automatically. We can decrease the risk of exposure, and we have a good revenue at the end about the money, because in the company the most important is to get money and to make money and to have a big profit at the end. And what are the problems that we can solve? We can solve the problem for interaction with the machine. We don't need a person or a lot of employees to check every machine. We can also remove the high travel cost, because the machinery can check alone the problem. We can have this process inside inaccessible places, and we remove all problem for employee. For example, we can think about a mining sector where there are machines in strong and hard place. We can get information in real time. We can change, and we can have always the efficient 100% for the machine. And that is most important for me, to active a process 24 hours per day, 7 days per week, without stop, we can check and control the stop for the machine. As I said, that's other problem that we can solve. We can have a proactive control. We can have a machine that configure themselves, increase, as I said, the efficient. And of course, we have a remote support or a remote assistance or remote job on our machine. What is the goals at the end for that? We can talk. We can see about a custom support, a work order support. We can give the satisfaction on the productive for the customer. We need always to have the right person, the right technician with the right skill, the right equipment at the end, without lost time, without have for a lot of time machine stopped. These are the advantages for connected services. We can reduce the downtime with the proactive alerts. We can reduce the maintenance costs because we send the technician. We can, as I said, stop the process only when the machine really need maintenance and support. And we can also be sure to have the right technician when the machine need help or need support. That's another part of the predictive maintenance or remote assistance. We can create a remote tech support, for example, for virtual reality or HoloLens, in this case with HoloLens, and the technician can work in a remote without have expensive costs for travel, without make a lot of travel, and they will be always proactive in, and the support will be in a short time without wait a long time to have a support. Now I would like to talk about our use case, predictive services on this time. I need to, that is our demo that we can use always in, to explain our company, the industrial digital transformation and predictive maintenance. The main actors are, of course, sensor, where we get all information, temperature, humidity, collision, movement, rotation, light. There are light sensor, etc., etc. All information are in cloud in our Azure IoT Hub. And we use Dynamics 365 to manage all work order and all IoT stuff. For dashboard and real-time telemetry, we use Power BI and Microsoft Portal to have a connection to communicate with support and with the customer. That is our case study. The request was to have a real-time telemetry in the main part in a machine, where that is for in manufacturing production sector. For each machine, we use 15 sensors: velocity, rotation, temperature, humidity, pressure, collision, and light. It's a multi-platform machine with C#, Python, C, C++ or C language, and we needed to create the right environment to manage that. Each production line has 80 machines, and that are in 3 different locations, with one monitoring central. The challenge was multiple machines, different language to communication, complex of data, different variable, and get the defect monitoring and defect preventive. The main criticism that we found in this project was the difficult to simulate the real situation, because we cannot test a real case, because we cannot connect directly for the test on the production line, but we needed to create a way to simulate with modeling, with data modeling, etc., our a real situation. That was the architecture. We have a 5-layer events, all sensor and machine. Collection are all our gateway. IoT platform, as I said, is related with Microsoft Azure IoT, Azure Stream Analytics, and machine learning. Action meaning all layer related with work order and customer service, customer engagement support. We use Microsoft Dynamics 365. And for presentation, for live telemetry dashboard, we use Power BI. That is events, device equipment with sensor production, produce data, and sense, of course. Collection, as I said, is all our gateway. We use IoT Connector Hub, and JouleHub multiprocess interface is our gateway. IoT platform is from Microsoft. Action is Dynamics 365 with Microsoft Field Services, and Flow to create automatic case and work order. And presentation is from Power BI. That is our predictive maintenance telemetry simulation, because, as I said, we cannot we cannot receive real data, real information. We create a noise, some telemetry as from our test devices. In this case, we have 10 features. Each feature is related with one noise, one sensor information, and each feature is related with one machine. That is the data that we receive. We receive one information every 10 milliseconds. That's why we need to have always under control and more detail for each sensor, each machine. And here we can see for example, in which axis, the temperature for one axis, for the timestamp, the rotation, etc., etc. And that is stream analytics from our Azure IoT, where we get the real query from all information that we receive from the sensors. We create with this data, and when the data lake is connected with the IoT hub, when we receive all information, we create this predictive machine user interface with artificial intelligence. We have for this project we create 85 layer, and each layer has for 38 steps. Here we are all process to manage and to analyze the data inside. That is another part for machine learning, sorry. And here is what we can see in our Dynamics 365 CRM in our Power BI. In Power BI, we have real-time telemetry with real-time performance and real-time calibration information, because, for example, this project is created to manage the performance, predictive performance, is managed to calibrate in the right way to have always the high performance to produce a circuit board. And here in Dynamics 365, we can see all IoT alert that we produce from our sensor. That is what we can see in our configuration. And that is a detail for an IoT alert, where we can see all detail from each sensor for each machine. As I said, we can use that for also for support. Here we can see, we can receive in real time a problem before to have this problem, and automatically the technician can understand where is the machine with the problem, how can move, what is the right way, way to follow for the destination, and what is the issue, what are the machine, what is the equipment that they need to replace and to adjust. And as I said, we can in our central, we can monitoring all machine. That is for Microsoft Portal, because it's most important Microsoft Portal to connect our customer with the company, because in this way you can understand the ticketing, you can understand what are the problem on your machine, you can understand also the status of repair, and you can understand how can manage this situation and the, if the ticket is solved or not. I prepare a small video where you can see if run, what a second. Okay, no, doesn't. Just 1 second. I prepared a video where you can see a demo, but I don't know why it doesn't work. I have to check. Just 1 second. Okay. I really don't know why it doesn't work. Okay, sorry, but I have a problem with the video, and I can share the video on the meetup on our social, and you can see the how can machine work and how can send IoT alert and how can predict and how can manage the performance. Thank you very much. That is a quick way how can see the digital transformation and how can create a performance way inside the company. If you have any question, you can contact me on this email or by website, or you can visit us in our offices when it will be possible.